Hi, my name is Jacob Bendel, and I'm a CPE.
Hi, my name is Hussein Mohammed. I'm an electrical engineering student at UCF.
Hi, I'm Anthony, and I'm a computer engineer.
I'm Christian, computer engineering, and we'll be presenting Object Detection Drone. Our object detection drone will consist of three things: the quadcopter drone itself, which will be made of modular and replaceable components, computer vision capabilities, which is the object detection part of our drone and encompasses object counting, and the companion application for the pilot, which will provide a live camera view and provide detection information. The motivation for pursuing this project stems from the team's mutual interest in drones as well as computer vision. It's a fun engineering project that encompasses both computer engineering and electrical engineering knowledge well. The goals of this project is to create an accurate detection model, reliable video transmission, fabricatable chassis parts, usable flight times, and intuitive controls. Our object detection drone will consist of three things: the quadcopter drone itself, which will be made of modular and replaceable components, computer vision capabilities, which is the object detection part of our drone and encompasses object counting, and the companion application for the pilot, which will provide a live camera view and provide detection information. The hardware block diagram on the left shows the basic relationship between the hardware components of our drone, and on the right is the chassis block diagram. These block diagrams show the division of work for which each member is responsible for. Responsibility includes research on the hardware selection, along with its application on the entire project. The drone subsystem of our project describes the physical aspects of our drone. In our quadcopter drone, we've incorporated the H-frame design using half-inch PVC pipes and T-fittings. This design is sturdy and offers enough space for other components to be safely mounted onto. PVC is strong, relatively lightweight, and cheap, all characteristics we want in the buildup of our drone. It is also very tineable and easy to work with. As you can see from the top view dimension picture, our PVC frame alone is a bit smaller than a sheet of copy paper. The next part of the drone subsystem are the motor mounts, which were designed in SOLIDWORKS and 3D printed. The motor mounts will be placed at the ends of each PVC pipe arm in a C-clamp manner and be secured by two sets of nylon nuts and bolts. The C-clamp design of the motor mounts were made to meet the modularity specification for a drone, and having it 3D printed allowed fast prototyping. The design makes it easy to assemble and adjust for proper motor balancing. It can also be easily removed, which is beneficial for portability and any possible replacement repairs. The long nylon nut serves a double purpose of securing the motor mounts as well as acting as the landing gear of the entire drone. The next 3D printed part is the body plate assembly, which holds all the components besides the motors. The assembly consists of the bottom and top plate with standoffs that connects both. The assembly is mounted on top of the vertical length of the PVC pipes via double-sided tape. The flight subsystem begins with the motor and propeller selection combination. A good rule of thumb to follow when selecting a combination is to have a minimum of a 2:1 to power-weight ratio. It is unnecessary for our drone to achieve much more than that, as our drone does not need much speed and will mostly be hovering. The brushless motor we selected is the Emax RS2205S and advertises a max thrust of over 1 kg. It offers great thrust for its size. Of course, that's in ideal conditions recorded by the manufacturer, but we should be able to expect at least 500 grams of max thrust per motor when paired with our propeller selection. As the kVs of other brushless motors can range from 2600 to 3000 kV, we've opted to go for motors that provides a lower 2300 kV as it draws less current while running more efficiently. The selected 5-inch propeller E6S3 has a pitch of 3.1, which is lower than most other 5-inch propellers, which usually range from 4 to 4.5. The lower pitch is expected to produce overall less max thrust and therefore less speed, but also draw less current since it cuts through the air more easily. This propeller in combination with our selected motor allows smoother and efficient flight compared to higher pitched propellers.
First of all, we have our flight controller. We chose the Naze 32 full version flight controller. It is basically the brain of the drone. It takes the input signals from our remote control through the receiver, takes that signal to the electronic speed controllers to regulate the RPM, orientation of spin, and the required voltage for every motor. Our flight controller offers an STM32 microcontroller that runs at 72 MHz processing speed. Also includes 10 degrees of freedom, meaning it offers a gyroscope, an accelerometer, a magnetometer, and a barometer. The two UART ports offered on this board come with a catch since UART1 cannot be used while not interfering with a micro USB. So we're mainly going to be using UART2 if we need one. And the micro USB is mainly used for programming or firmware updates. The total weight of this board, including the soldered headers, was 7.3 grams, and it cost us $19.99. This table shows a comparison of the flight controllers that we researched. Our top choice was the Naze32 flight controller, mainly because it provided the sensors that we needed at the best cost. Granted, it's not the best CPU out of the 3 flight controllers, however, it was sufficient enough for our needs. Next part of our flight subsystem is the electronic speed controllers. The electronic speed controllers, as mentioned earlier, regulates the RPM, orientation of spin, and the required voltage for each motor. The current rating of our chosen ESCs is 35 amps. We chose 35 amps because the motors are going to be drawing a max current draw of 25 amps, so we left 10 amps room for error and for safety. These ESCs take an input voltage of 2S to 5S LiPo cell battery. We have a 4S LiPo cell battery, so we're going to be using the battery voltage directly. The weight of each of these electronic speed controllers is 5.98 grams, and the total cost of all 4 was $47.99. Next, we have the battery. We chose to go with the HRB lithium polymer battery. It's a 4S battery, meaning 4 cells, which is 14.8 volts. The capacity on this battery is 3,300 milliamp hours. It's got a discharge rate of 60 C. Based on the calculations shown on the slide, it provides 11.77 minutes flight time, and this battery weighs 318 grams and it costs $37.99. Next in the power subsystem is the power distribution board. We obtained this design using Texas Instruments WeBench Power Design. This is a voltage regulator design using the TPS 56339 DDCR integrated circuit. It's a buck switching regulator. It will take 14.8 volts input off our battery and output 5 volts out. And based on the website, it is 93.1% efficiency. The design we obtained from Texas Instruments WeBench Power Designer was modified to include 4 extra battery voltage outputs. 1 will be used for the actual battery, and 4 will be used to take the battery voltage to the electronic speed controllers. The regulated output voltage is 5 volts, and that will be used with our Naze32 board. For our PCB portion of the design obtained from the WeBench website was implemented as a PCB design using Autodesk Eagle software. As you can see, thicker traces were drawn, leading to all our high power loads. This is because they require more current and they'll produce more heat, so the smaller traces that are shown in the center of the board would not suffice for the larger pads on the outside of the board. Pads were placed on all five VBAT connections, all our battery voltage connections, and a smaller pad on the 5 volt out connection. Each pad has a corresponding ground pad, and to facilitate heat dissipation, the top and ground layers include planes to act as a heat sink. Our top plane is a ground plane which is connected to all our ground connections, and the bottom layer includes a VBAT plane that is connected to all our VBAT connections. That way we can use them as heat sinks and prevent the board from overheating.
For the detection subsystem of our project, we decided to utilize a video camera for the improved ability of object detection and piloting the drone without needing to have a line of sight. We chose the Mobius Action Camera because of its common use as a dash cam. It had the ability to transmit its video signal using other transmission methods besides Wi-Fi due to Wi-Fi's lower transmission distance. The ability to offer various resolutions let us experiment with the resolutions to see which benefited the object detection the best, unlike the lower resolution of the Beta FPV Z02 camera. The main resolutions that were offered by the Mobius Action Camera were 1080p at 30 fps and 720p at 60 fps. The camera also offered 720p at 30 fps, which we decided to utilize in the end. For example, the time it takes to process the detection and the latency for the video transmission could have been affected by the pixel or frame counts. The camera also offered the ability to output the video and or audio, which we utilized using the video transmitter. One of the reasons we chose the Mobius Action Camera was because of that ability, which other cameras lacked, such as the GoPro Hero camera. The computer software let us configure the camera to the 720p at 30 fps resolution we decided to use, along with modifying the image settings as needed. With a weight of 1 ounce and a size of 1.38 by 2.4 by 0.72 inches, the camera was able to be lifted by the drone easily and also able to be mounted without taking up a significant amount of room on the drone for other components. The camera was also able to be modified to a different output configuration. By shorting pin 4 with pin 5 of the mini USB port, pins 2 and 3 were switched to video and audio out pins respectively. That gave us the ability to connect the camera straight to the video transmitter on the drone. To go along with the chosen camera, we also decided on the Eachine TX805 video transmitter and the Eachine ROTG02 video receiver. We decided to not go with onboard processing of the video due to the limited processing power that we could achieve with our budget. Since we were wanting to utilize a phone for the receiving of the video feed to make piloting easier, we came up with the idea of also using the phone to process the video, since a phone has an adequate amount of resources that is able to be utilized. With a transmission range of over 3,000 feet, the transmitter met our requirement of at least 50 feet operational distance from the pilot. With a weight of around 0.3 ounces and a size of 1.42 by 0.87 by 0.2 inches, the video transmitter was able to be lifted by the drone easily and also able to be mounted without taking up a significant amount of room on the drone for other components, much like the camera. The Eachine TX805 was compatible with the Mobius action camera by joining the respective wires from the camera to the appropriate wires in the video transmitter as seen in the schematic on the right. The 7 to 24 volt and the ground connection point next to it were connected to the battery via the PCB, while the video, second ground, 5 volt, and audio connection points were connected to the camera as seen in the image to the left. The voltage input range was able to withstand the voltage from the battery that we chose to use. We opted to not include the audio connection due to the possibility of issues involved with audio. The antenna included with the transmitter connected straight into the transmitter and was also not significantly long where it would be able to be positioned on the drone in an appropriate way. We could have chosen the TBS Unify Pro 32, but the deciding factor for us was the significant cost difference between it and the other transmitters. We could have also chosen the Go Quo Tomo E600, but the weight was significantly heavier than the Eachine TX805. We chose the video receiver for two reasons: the ability to connect it to a phone to view the video feed from the drone, and also the compatibility with the video transmitter. To control the drone, we decided on the FlySky FS I6X controller and the included FlySky FS IA6B receiver. One of the main reasons we decided on the controller and receiver was the cost, since it was able to fit within our budget. With a transmission range of around 3,700 feet, it met our requirement of at least 50 feet operational distance from the pilot. The controller had 6 channels where each channel could be utilized by a command. For example, the commands for throttle, turning left and right, pitching forward and backward, and rolling left and right each utilized one channel. Even though the controller had the ability to use 10 channels, we were able to utilize up to 6 instead, since the receiver had 6 channels. The receiver was included with the purchase of the flight controller to ensure the compatibility of the two components, and the receiver was also compatible with the flight controller and was connected using wires and the connection points as illustrated in the image.
The entire drone was modeled through SOLIDWORKS to help plan the component placements. The custom model 3D printed parts are the motor mounts and body plate assembly. The rest of the components were sourced from GrabCAD and modified as needed. Dimensions, tolerances, and mass were made as accurate as possible for more clear expectations in the 3D printing and assembly phase. The 5 main components of a drone must be able to support and carry are the battery, camera, flight controller, PCB, video transmitter, and controller receiver. These components will be mounted on the 3D printed body plate, which itself is mounted on the PVC frame. The heaviest component is the battery and will be placed at the top of the plate for ease of access and overall balance. The flight controller and PCB will be mounted on the top face of the bottom plate and the video transmitter at the bottom face. The camera and controller receiver are mounted at the angled end of the sides of the bottom plate. As most of the ESC wiring is routed through pipes, this compact configuration allows easy access to each component and keeps the wiring clutter to a minimum.
Now that we've gone over all of our major systems separately, it makes sense to see how they're all connected together. This is our overall schematic. The power distribution board is depicted in the center, providing distribution for our main power source as well as 5-volt regulation for other components. Our motors are depicted on the outer perimeter and are directly attached to the electronic speed controllers, or ESCs, which allow us to dynamically control their speed. Communication between the ESCs and the Naze32 flight controller is handled via the DShot protocol. This is a digital protocol unlike analog ones such as PWM. In order to control the drone from the ground, there's the 2.4 GHz receiver connected directly to the Naze32 flight controller. This takes input from the RC controller in the hands of the pilot. To the right of our schematic is our detection system. This consists of the video camera as well as the video transmitter. This is not connected to the Naze32 flight controller, but is its own separate system.
Our estimated SolidWorks and table mass weights come to a bit over 1,000 grams. Our actual measurements without all the wiring comes to about 1,100 grams. This guarantees our minimum of 2-to-1 power to weight ratio requirement.
Now that we have covered the hardware systems and capabilities, our companion pilot application will take over the main responsibility of object detection. For our application, we chose to use the Android platform and will be developing primarily with Java. The pilot application will provide a live view video from the drone such that the pilot can see what the drone sees. Additionally, it will utilize any Android smartphone to offload the machine learning tasks of object detection and counting. This means we don't have to use any additional hardware to complete those tasks. This is the high-level block diagram of the pilot application. External to the application itself is the hardware video receiver. This will connect to our pilot's phone via a USB cable. The app will then have to receive the video, process it, and provide it to our real-time detection algorithm. From there, the GUI will be updated as necessary to reflect any results from the algorithm.
There were originally 3 paths that we had available to capture our video input for the detection algorithm, but ultimately we decided on a 4th. The first was our preferred path that consists of Eachine, the manufacturer, providing us a driver to directly interface with the video receiver. However, our initial attempts to propose this had fallen on deaf ears and we have not received a response from Eachine. We pursued a second option of reverse engineering the provided Android APK. By decompiling the APK, we were not able to discern any viable information for taking the frames directly from the receiver. This was due to obfuscation that comes with decompiled code. Third, we tried screen recording the drone's flight view from the provided APK. We were using the Draw Over app feature provided in Android to capture frames from the Android display. This would have worked similarly in principle to a screen recording app. All of these were for nothing, as eventually we decided on a 4th and easier method. The provided Android app for the receiver saves video of the flight, and we would be able to instead work directly with this saved video. This was useful as it provided a direct path to the frames and no longer relied on workarounds. Some of the technologies for our application had been set in stone from early in the project, while others had come after finalizing our development path. We chose to develop our application for the Android platform due to its widespread support and use of Java, a language we had already been familiarized with. Once we knew the target platform, choosing a library for real-time object detection on a mobile device boils down to either OpenCV or TensorFlow Lite. Out of the two, TensorFlow Lite was much smaller in overall size and is more dedicated to machine learning using models versus general computer vision tasks ultimately found in OpenCV. Lastly, we needed a way to manipulate video files. This was accomplished via the FFmpeg library. It provided us a means to parse individual frames from a video and then recombine them later after detection. This is how the pilot will interact with our application. Ultimately, the pilot will launch our application, which runs our detection service in the background. When the hardware receiver is plugged into the phone, the provided FUAV app will be launched. The pilot can start a video during flight and stop it within this provided application. Once safely landed, the pilot can return to our pilot application. Here they will be shown the detected video clips from their previous flight along with stats from the detector. Additionally, the pilot has a convenient interface for video playback and deletion of unwanted clips. In order to provide the desired functionalities, 3 main classes will be needed: a GUI, a detector, and a video handler. The detector class will receive frames from the video handler that has parsed the in-flight video. Real-time object detection on each frame is done in the background while removing visual clutter so the pilot can safely land the drone. These process frames will have bounded and classified detections for a given object. In the class diagram, we can see that this producer-consumer relationship is modeled as a direct dependency. Once the detection is completed, the frames are then encoded back to a video file for view in the application's GUI. We chose to use the Coco SSD MobileNet V1 model for our object detector. This model was well documented and had a portable size of 27 megabytes. Compared to the MediaPipe Objectron, we were really only looking for 2D inferences, as 3D detectors on mobile platforms are relatively new and undocumented. The inference time for each frame is lower on the MobileNet V1 than that of competing mobile 2D detectors, like YOLOBIL. This is explained via the vast difference in model size. As we can see, YOLOBIL uses a larger, more accurate model at the cost of inference time. Let's take a look at the process described in the use case, what our pilot will see and do. Here's the FUAV application that ships with the Eachine video receiver. When the phone is plugged into the receiver, the application is automatically launched. The pilot can view the video feed from the drone on their phone mounted to the controller. To interface with our pilot application, the pilot in command simply has to click the Record Video button. After finishing the recording and safely landing the drone, the pilot can open our application to find previously detected clips as well as the one they just took. When selecting a clip, media playback will start. Additionally, detector metrics such as the inference time, number of detections, and thread used will be displayed. If the pilot has no further need for the clip, there is convenient UI for deleting the video from the device.
One stretch goal we had is to create a GPS recovery system. This feature would be useful in an event of a crash where the GPS module can gather the drone's current coordinates and have the MCU send the data via SMS to the pilot's phone. GSM and GPRS are just 2D technologies. We wanted to use them because they are common and cheap in many industries for SIM card-based messaging like text SMS. It also has a much better range than other technologies. The module will use an AT attention command to send SMS messages to a specified number. Because our drone can operate at 400 feet or even further and can be lost or stolen, it's better to use cellular over Wi-Fi or Bluetooth. We chose the GTU7 module because it has a faster fix time, meaning that it can get the first GPS readings / coordinates quicker than our other consideration. It is also cheaper and have good support for the Ting GPS library. The Ting GPS library is a useful library for interfacing with GPS modules and does things like parse NMEA strings, which is the standard formatting for GPS messages. We were ready to use either of these MCUs but chose the ATmega 2560 as we wanted the 4 UART channels to talk to our sensors as well as the function to debug with a PC at the same time. Another big draw was its easily available libraries, as mentioned before. The sizing, weight, and frequency were not much of concern as they were essentially the same. We ended up settling for a proof of concept test using the chosen GPS ATmega 2560 MCU and an HM10 Bluetooth module. Major US cell carriers canceled legacy services for 2G, and 4G module shippings were weeks away. Time simply ran out. Battery, drone, and additive manufacturing are the 3 main types of standards related to our project. The battery standards describe the proper disposal of LiPo batteries. The drone standards and constraints describe flight constraints as well as safety and filming regulations. The additive manufacturing standard relates to our 3D printing processes.
We decided to set our budget to be $500 or less. We did seek out sponsorships but received no response, so each group member has purchased different parts depending on what each group member has researched. We did not exceed our budget. Some of our successes with this project were our early PCB design and the fact that we ended below budget. We also had clear goals on the path of our project and how we were going to succeed. We were able to adapt to challenges that we ran into, and were still able to complete everything on time. One of our difficulties was having to reorder multiple devices, such as the camera and ESCs. We initially purchased a counterfeit camera, which resulted in the camera not connecting to the computer for configuring. When installing the ESCs while finalizing the drone, we broke a piece off of 2 of them, and our attempts at repairing the devices were unsuccessful. That resulted in us having to order more and not being able to finalize the build of the drone until after the new ESCs arrived. We also initially reached out to a PCB vendor and were going to continue forward with them until they gave us an outrageous price, so we had to quickly switch vendors. The SMD soldering was challenging since all of us didn't have extensive experience in soldering and the components were very small, which was a cause for easy bridging. We also had to redesign our PCB slightly and then order the updated design with enough time to be able to utilize it with our final product. Then, of course, COVID had increased delivery times for parts from overseas, which caused us to have to either look for alternatives or just end up waiting longer than we had hoped. And the project is complete. Does anyone have any questions?